Okay, good morning, everyone. Thanks for braving the snow. Orientation, you're working on 5, 9, and/or 10. For the grads, I will talk next Tuesday about what happens after A10. Any questions about the assignments? All good? Okay, right back to it. We are working our way through the first sets of experiments that establish the field of evolutionary robotics. And we started in last time in lecture 9 on 4 sets of experiments collectively called the minimal cognition experiments. The overall goal or approach of the minimal cognition experiments is to conduct a physical Turing test, to create machines, simple machines, minimal machines, that move about or act in a way that you would attribute intelligent action to them. Remember the Bradenberg vehicles, we observe these machines and we attribute intelligent behavior to them. In minimal cognition, they're going to evolve 4 different building blocks of intelligence, and we started talking about the first of those 4 last time, which is the ability to reason about objects near you, to think about what those objects or those things afford you. These things afford sitting, this thing affords writing, or under certain circumstances, stabbing. Yes? So we're thinking not just about the geometric properties of objects, but about their relationship to us. That's what affordances are all about. And we introduced at the end of last lecture the first minimal agent that has 2 motor neurons that control 2 rockets that push the robot back and forth along the bottom of a 2-dimensional screen. And there are 7 sensor neurons assigned to 7 proximity sensors, and those 7 proximity sensors at any moment in time in the simulation provide a floating point number about how long or how short that the distance is between that proximity sensor and whatever else is out there in the world. All of the minimal agents that we're going to see in the minimal cognition experiments, they're controlled by CTRNNs, right? So remember, underneath, we've got a set of ordinary differential equations, and evolution is going to tinker with the parameters or the coefficients of those ordinary differential equations, which alters the way that those neurons continuously change value over time in response to the values of other neurons in the CTRNN and the 7 sensor values. So far, so good? Stage is set? Okay, off we go. So we're going to evolve a population of CTRNNs. So we have a set of ODEs that describes one CTRNN. Then we have a second set of ODEs which have exactly the same form that we saw in the previous lecture, same mathematical form, but have different random coefficients. Remember, an evolutionary algorithm always starts by creating a population of random things. In our case, this is now going to be populations of random CTRNNs. And when I say a random CTRNN, I mean a set of ordinary differential equations with randomly set coefficients. So far, so good? So we've got a whole bunch of random brains. We take each brain and drop it into our minimal agent at the bottom, and it starts moving left and right along the bottom of the screen. And as it does, a pair of objects starts to fall at a constant velocity straight down, which is what's represented by this dashed black arrow here towards the bottom of the screen. The fitness function, which we're going to talk through in a moment, generally speaking, is going to reward agents that perceive affordances. How are we going to know that the agent perceives affordances? It doesn't have a mouth. It can't tell us. It's going to try and pass the physical Turing test. It's going to act as if it can correctly perceive the affordances, the affordance of this pair of objects, or what this pair of objects affords it, which is this pair of objects either affords a passageway between them that is wide enough for the robot to get between them, or a pair of objects is going to fall that projects an affordance that says, I am not passable to you. The distance between the 2 objects are close enough that the agent cannot pass through them. Okay. For each random CTRNN, we're going to drop it into the agent a number of times. We're going to do a number of trials. So we're going to evaluate each CTRNN num trials times. During these different trials, it's going to be exactly the same CTRNN. We're going to put it inside the robot. We're going to start the simulation, but we're going to drop different pairs of objects. Some that are too narrow for the agent to pass through, and some pairs of objects in which the gap between them is wide enough for the robot to pass through. In the cases where the gap is wide enough for the robot to pass through, the fitness function is going to reward that CTRNN for getting the robot to move underneath the pair of objects such that one object falls to the agent's left and the other object falls to the robot's right. That the robot shows us that it knows the gap is passable by passing between the pair of objects. In some of these trials, we're going to drop a pair of objects in which the gap is too narrow for the robot to pass through. In that case, the robot should figure it out and then run as far to the left or right as possible. Be as far away from the pair of objects when the objects hit the ground as possible. That's what the fitness function is going to select for. So far, so good? Okay, so we're going to compute, in this case, not F for fitness, P for performance, means the same thing. So we're going to sum up the average performance of one CTRNN over a number of trials. So P sub I is going to represent the performance or how well the robot did during the ith trial. In cases where the opening between the pair of objects is too narrow for the agent to pass through, so the affordance that's being projected is impassibility, we're going to set P sub I to 100 points. This is going to be the maximum score if the robot does not collide with the wall. So if the gap is too narrow, the robot should move out of the way and let the pair of objects hit the ground, and the agent should be nowhere near the object pair at that time. The agent is going to get these many points if when the objects get to the ground, the agent is near enough that the agent collides with, wall is not the right word here, with either of the two objects. We're going to compute the value set to P sub I to be 2 absolute D sub I, where D sub I is the final horizontal separation between where the objects hit and where the agent is at that time. There's a typo in this equation. Distance is always, D is the final horizontal separation. So if the robot is far to the left, that D sub I might be negative. And if the agent is far to the right when the objects hit, D sub I might be positive. So we're taking the absolute distance between, the horizontal distance between the robot and the object pair. What is this term selecting for? A fitness function selects evolutionary pressure that pushes the evolving population of CTRNNs towards a particular behavior. What? What kind of behavior does this reward for? We want P to be larger.
Being as far away from the walls as possible.
What's the worst thing a CTRNN could cause the robot to do, given this term?
Get hit by one of the blocks. Or meter next to it.
Yeah, can we be a little bit more specific? What's the absolute worst thing according to this term? What do you have to do to get no points? You get 100 points if you don't get hit.
To not move and like it's going to hit you and you don't move.
Not necessarily not move. D sub I is the final horizontal distance. So we might drop the pair of objects above and to the right of the robot, and the worst thing it could do is get right underneath and get hit such that D sub I is 0. It's exactly right underneath the object pair. That's the worst possible thing we can do. So when the gap is too narrow, this term is selecting for run away if the gap is too narrow. Everybody see that? Okay, remember we're going to do this a bunch of times for each C tier and N. So sometimes the aperture is going to be wide enough for the agent to pass through. And in that case, we're going to compute the performance during that trial, the ith trial, using this equation. And this, I remember now, this equation does have a typo. So there's 3 conditions here. So if the robot is beyond the blocks, if the gap is passable, and the robot runs away, it's doing the wrong thing. It's quote unquote interpreting the affordance incorrectly. The robot is acting as if it thinks the gap is impassable, but in reality the gap is passable. Maximum points if the robot gets between the objects and one object falls to the agent's left and the other object falls to the agent's right. And this kind of clumsy term here, if the agent collides with the wall. What if d sub I is 0? What does that mean, and what does the robot get in terms of p sub I in this case? The gap is wide enough for the agent to pass through.
It gets 80.
It gets 80. Yeah, that's right. So it's doing the right thing, but it got hit by the wall a little bit. So actually, it can't get d sub I of 0, because if d sub I was 0, it would be directly underneath the object pair, and it wouldn't get hit, because by definition, the gap is wide enough for the agent to pass through. So if it's underneath the blocks and it's kind of wavering back and forth and gets hit by one of them, p sub I is going to be set to this term, which this term starts to give more and more points as d sub I gets closer and closer and closer to 0. Everybody see that? So if you're kind of outside and you get hit on the outside, that's pretty bad. If again, another C tier and N gets hit, but now it's closer to the center of the block pair, you get a little more points, until eventually a C tier and N evolves that doesn't get hit in this case. Let's go back to this term for a moment. What would an agent be doing if it gets a p, not a p sub I, of 100? What was that C tier and N causing the robot to do?
Doesn't collide with the blocks.
Doesn't collide with the blocks. That's true. A C tier and N that causes the robot to always run away, regardless of whether the gap is too narrow or wide enough, would also not get hit, but would not get a p of 100.
Going through the gap as well.
Going through the gap as well, right? So when the gap is wide enough, be right underneath the object pair, and when the gap is too narrow, be as far away, or at least be far enough away that you don't get hit. Assuming such an agent evolves in the population, that's the agent passing this particular physical Turing test. It's showing us, not telling us, that it understands the particular affordance of this particular block pair. It's sort of arbitrary, very simple, very specific, but we're going to proceed in the minimal cognition experiments in this way. Start simple. Okay, it's a lot of lead up. This paper is 26 years old at this point, but still a classic in the field. So unfortunately, no fancy YouTube videos. We're going to have to interpret what evolution did using some technical figures. So at this point, we've now run the evolutionary algorithm. We had 100 random C tier and N's. We dropped each C tier and N into the agent N trial times, computed P. As you would expect, the robots kind of move around randomly at the bottom of the screen, sometimes get hit, sometimes don't. They get a P that's very, very close to 0. But some C tier and N's in that population of C tier and N's get a P that's slightly higher than 0. Those C tier and N's survive. The other ones are deleted by the evolutionary algorithm. The evolutionary algorithm makes randomly modified copies of the surviving C tier and N's. What does that mean in this case? It means we take all the coefficients for the surviving C tier and N, We copy those coefficients, and then mutation randomly changes some of those coefficients. Some of the taus go up or down by a little bit. Some of the w's go up or down by a little bit. Some of the g's go up and down by a little bit. And some of the thetas randomly go up and down by a little bit. Those child C-ternns, when dropped back into the agent, still cause the agent to mostly move randomly, but maybe, like their parents, those C-ternns get a slightly higher value of p than 0, and maybe even a slightly higher p-value than their parental C-ternns. They survive, produce offspring, and so on and so forth. Yeah? Getting you to run the evolutionary algorithm in your head. Okay, at the end, they obtained a robot. They obtained a robot that they obtained a C-tern that when dropped into the robot, and we dropped whole bunches of object pairs from above, would get a p-value very close to 100. Remember, an evolutionary algorithm is a satisficer, not an optimizer. We're never promised to get back a C-tern that gets a perfect score. It's very close to 100. So what does that C-tern cause the robot to do? In all the minimal cognition experiments, we're going to see visualizations of the champion, the C-tern with the highest p-value ever found. Okay, so imagine we take this C-tern and we drop it back into the agent, and one after the other, we drop a series of object pairs, some of which have an aperture width that is relative to the agent's diameter are negative. So negative relative aperture width means the width is narrower than the width of the robot's body. A relative aperture width of 0 means the gap between the falling pair of objects is exactly the same width as the width of the robot. A value of 4 means the aperture width is 4 length units. We're dealing with a physics engine, so things are kind of, there's no units here. The aperture width is 4 units wider than the robot's body. The horizontal axis here is plotting for that C-tern the average final horizontal separation between the agent and the object pair when it hits the ground. And by average, I mean, in this case, they dropped a whole bunch of object pairs in which the width was 4 units narrower than the agent's width. And they dropped that object pair from different horizontal positions at the top of the screen. They want to see in general how well does this evolved C-tern do. Okay. The vertical bars that you see here, this is reporting error estimates, error of the mean. So uncertainty about the average final horizontal separation when we drop pairs of objects that are 0.1 width wider than the width of the agent. Okay, hopefully I've given you enough information to be able to parse this graph. What does this C-tern cause the robot to do in general? I already gave away part of the punchline, which is it's not optimal. It's close, but not quite. None of us are. It's okay. How? How is it non-optimal? It's pretty damn good.
When the aperture width is pretty close to 0, it has a wide variability of what the distance away. It can't quite tell whether it is or not, so it'll just make a decision.
Yeah, it'll make a decision, right? So at this point here, this is kind of tricky, right? The gap in reality is passable, but just by a little bit. Sometimes the robot runs away and the final horizontal separation is large, and sometimes it says, I'm going for it. And it does it. Sometimes not. Sometimes it gets hit.
It's just interesting to me that that's only on the one side.
Exactly. So let's look on the other side here, this point here. So here the gap is just a little bit too narrow. What does the robot do in this case when the gap is just a little bit too narrow to get through? Get the heck out of the way. What about this point right here, which is when the width is just right? Exactly the same. What does it do? Mostly runs away. Remember Bratenberg vehicle 2A, the coward? This is kind of the coward also, right? This robot, armed with this C-turn-N, tends to err on the side of caution. It's usually running away. There's an asymmetry here. I'm describing that like it's a non-optimal thing to do, but most of us are here because our ancestors also tended to err on the side of caution. When you're not sure, assume a threat. So that's usually a better strategy on average than if you're not sure, assume a friend. So non-optimal, but maybe as good as possibly can be done. Yeah? Okay. Okay, I love the minimal cognition experiments for lots of reasons. One of them is that they really get out the microscope and look at evolved behavior. So we're going to look in these two plots now at exactly the same C-turn-N, but we're going to zoom in on this sort of cautious behavior. How exactly is the robot moving, and how is it deciding whether the gap is passable or not? So let's start with this panel over here. Each one of these black horizontal lines corresponds to one simulation, one trial, in which they drop the pair of objects where the aperture is 1 unit smaller than the agent on the left. So in all these cases, the aperture is too narrow for the agent to thread the needle. Okay, here's how to read this plot. We always want to understand the axes first, so let's tackle the horizontal axis. The horizontal axis reports horizontal position. This is the horizontal position between the agent and the horizontal position of the blocks. Yeah? As the blocks are falling, the blocks always fall straight down, but remember the agent is moving left and right along the bottom of the screen, so the relative horizontal position between the object pair and the agent is changing over time. The vertical axis also kind of represents time, but it's directly reporting vertical position, the height of the object pair. You'll notice that all of these black lines start out evenly spread at 140. What does that tell you about these, I don't know, what is this, 25, 30 trials? How do these 25 trials start?
With the object pair and the robot at like different positions each time.
Different horizontal positions at the top of the screen. So this one over here, they put the object pair at a height of 140, and they place it 40 horizontal units to the left of the robot. This trial right here, they start by again putting the object pair 140 units above the agent, and they drop it almost directly above the agent. Everybody see that now? Okay. What does it mean for segments of time in which the trajectory, the black line is mostly vertical? What is that telling you about the agent's behavior at that time? What is the robot doing at that time?
Stationary.
It's stationary, right? Horizontal position is not changing. Remember, the blocks always fall directly down. What do diagonal lines mean? The robot's moving. Okay. What is the robot doing in these cases where the gap is impassable? What can you tell me about how the robot is moving? What's its strategy?
It moves to the edges.
It moves to the edges. So in every single one of these black lines, they all pass the midpoint of this plot at some point, right? So there is some point in which the robot passes directly underneath the object pair, and in some cases it then heads west as far as it can, or heads east as far as it can, which is what you would expect in these cases. Or at least you want it to get out of the way. Doesn't have to move left and right. Could always have moved to the left, could always have moved to the right. It's just what happens in this case. Question?
Does it have to get under the object pair to know the distance? Is that why it's going under? Is it just doing that?
Great question. So I haven't given you enough experimental details to answer that question, which is how far can the proximity sensors reach? I will tell you, they can't reach all the way. It can't see an infinite distance in here. So there are places that the pair of objects can be that the robot can't see the pair of objects. Question?
Seems like there's a discrete number of ray casts, and they have quite a distance between each other. So maybe an evolved strategy is moving to get better resolution. I know LiDARs do that.
Great point, right? So this robot is, again, it's minimal. It's almost blind, right? It doesn't get this beautiful Technicolor, field of view. It's getting 7 numbers at every moment in time. So it's possible that it's moving in order to upsample the resolution of its perceptual abilities. We also do this all the time. Autonomous vehicles do this. It's a common trick in nature and now in technology. Good question. Second, a follow-on question is, does it need to? For this task, hard to say. For those of you still thinking about final projects, students in the past have tackled some of these minimal cognition experiments, or they come up with their own versions in PyBullet. Then you could explore some of these questions. Good point. Okay. Let's look at the right plot where everything is exactly the same as you saw before. Same CTRN. They're going to expose it to a bunch of new conditions, which is now they're going to drop object pairs in which the gap is 1 unit wider than the agent on the right. What does the agent do when armed with this CTRN in these cases? What does it do similarly? What does it do differently?
It's moving to the center relatively the same way as it had been in the other positions, and then occasionally it seems like it maybe moves a little out, but then just each time it comes back in and it stays in the center.
Okay. So it's moving around basically identically to how it moves around in the presence of impassable objects. And then at some point it stops and it's kind of showing off. It's directly underneath the objects while the object pair is still 40 units above it, and it just stays there and waits. It's already solved the task. It, quote unquote, knows that it solves the task. I'm going to put a lot of words in scare quotes this morning because, again, we don't know. The agent is acting as if it knows that it's solved the task. When does this agent, when and where does this CTRN make a decision about whether the gap is passable or impassable?
Like 60.
Why 60?
Because at that point, it either tends to just go straight or it diverges.
Okay, right. So it's at about this height, 60 or 58, where these two plots look differently. That the agent starts to behave differently in the presence of passable and impassable object pairs. So you're proposing that's when it made the decision. Everybody okay with that? I see a few people shrugging. Good. Thinking about thinking is misleading. It looks as if it's made the decision at this point and immediately starts showing us that it's made the decision by acting differently and actually acting appropriately in these two different conditions. Remember the R in CTRNN. Hint, hint. What does the R stand for? And why does that matter here?
Recurrent, and it's sort of like the decision period is like getting smaller and smaller, sort of like in like a control theory kind of way. Like it's
The window in which it needs to make the decision?
yeah.
Okay. What do the recurrent connections in a neural network give the robot, give it the opportunity for? For memory. It's possible that before 60, when the objects earlier, It's possible that the robot has already determined that the gap is passable or impassable and is holding on to that memory somehow, but that memory is not yet affecting the motor neurons and the rocket thrusters, right? You do this all the time, or at least it feels like you do this all the time. You've made a decision about something. You're either going to go to your next class or you're going to skip it, but there's no outward behavior showing that you've made that decision. So it acts as if it's made the decision around here, but it's impossible for us to say, at least at this level of analysis. We could possibly go in and start dissecting this evolved CTRN to see if we could figure it out. We can't know. But the robot definitely has, quote unquote, decided, because it acts differently under these different conditions. So far, so good? Okay. Looking pretty good so far. Yep.
So under like that 0.60, you still kind of got a little loop where it moves a little to the side and then comes back in. Do you think that might be related to what Yoon was talking about it being potentially moving back and forth to get a better resolution of it?
Yeah, great question. So you're talking about this little hiccup here, this little sweep back and forth. So great question. Evolutionary biologists ask this question all the time. You take some behavior or some feature of physiology or anatomy and say, is it actually serving a purpose for the animal, or in this case, for the agent? Is that little sweep back and forth, is it sort of confirming what it thinks, quote unquote, making sure that it knows whether it's passable or impassable? Or, remember, the fitness function only cares about when the object pair gets to the ground. What the robot does before the object pair gets to the ground is not factored into this calculation. So it's possible that this is just a second order effect. It's just kind of a epiphenomenal. It doesn't actually help the robot and also doesn't hurt it. So there's no reason for the evolutionary algorithm to get rid of it. Yeah? There used to be a long debate for decades about our appendix, right? Like, what is it for? It seems to kind of be a problem for some of us some of the time. Like, is it actually doing something useful, or is it just kind of left over? It's a byproduct of something else. So lots of examples of that in nature as well. It's possible that this is one as well. You could always go in and force it to not do this and see whether it then gets a lower value of p, right? We could start to intervene on the agent to see what happens. And we'll see examples of that later in the course. Good question. Any questions more about these two figures before we move on? Okay, these authors are very rigorous. So they went back, took the same CTRN, dropped it back into the robot thousands of times. The nice thing about working with a very simple simulator like this, it was really fast, even way back in the Stone Age. They dropped it thousands of times so that every individual pixel in this figure now represents one trial. Okay. A white pixel, the pixel is colored white if the robot did good, if the robot did what it was supposed to do under those conditions. Impassable gap, run away. Passable gap, thread the needle. Black represents that the robot did the wrong thing. So if the gap was passable and it ran away, or the gap was impassable and the robot tried to get underneath the object pair. And gray is mediocre, meaning the agent got hit by one of the two blocks. In either case, if you get hit by the block, you're doing the wrong thing. Okay. Horizontal axis is initial horizontal position. So the agent always starts at the midpoint on the ground, and the object pair is placed at different horizontal positions above. So like up here, this horizontal axis is the same as this horizontal axis down here, except it's the initial horizontal position. Everybody see that? Vertical axis is now representing relative aperture width. So the bottom half of this figure represents dropped object pairs that were impassable, and the top half of this figure represents object pairs, dropped object pairs that were passable. Tell me about the bottom half of this figure. What's going on?
It's just moving out the way.
Remember, we're dealing with kind of the coward here, right? So in almost every case down here, the robot is always running away, which is the right thing to do. Good, white, done. Okay, tell me about what's going on in the top half of this figure. First thing you should notice is obviously not so good. Remember, the top half is passable gaps. In theory, the robot should be able to thread the needle. What's happening?
So if zero's supposed to, I'm assuming zero's then passable in the top half, or is that?
Zero is, you know what, it's not clear. Probably not passable, actually.
Because it seems to just fail every single time. Like, must be like just close enough that it looks like it can pass it, and it tries and then fails.
Yeah, maybe. Hard to say it exactly zero, but a little bit above zero. This is passable, and it's black. So what's going on there? What's the robot doing?
If it's just above passable, then there's a very small window for the robot to actually be able to make it through.
Yep.
So it's probably just like scraping the wall or like
Scraping the wall is gray.
oh,
So black is not. Black is the robot didn't get hit. The gap is passable.
it's deciding wrong and running away when it could be.
It's running away when it shouldn't. Right there. That's the cowardice piece here. What else is going on in the top half of this figure?
The initial horizontal position is pretty important.
Yep. Because right here, if they drop the object pair directly above the robot, and even if the gap is super wide, more than enough room to get through, the robot runs away. Bad. And then all these other regions where it's quote unquote not sure what to do. It doesn't quite run away, it doesn't quite get directly underneath, it's getting hit. Remember, this is the best evolved solution, a solution that had almost p equals 100. What's going on? Why so many mistakes? We train an autonomous vehicle on roads with live humans, gets a score of almost 100. We're like, great, all right, off you go, Burlington, San Francisco, downtown Manhattan, and then this starts happening. Not good. What's happening? Why? How can this happen?
Could it have been overfit so it was performing really well with like what it was trained on, but now that it's got new data, it's not generalizing well?
Exactly. It's got new data. There are many, many pixels here that represent environmental conditions that evolved C tier and N never saw during training. We would usually say in machine learning. In this class, we're going to say during evolution, which basically means the same thing. I didn't really tell you exactly how many NUM trials there were. This shows you what NUM trials looked like. These were the conditions that the agent, the C tier and N did see during evolution. Why the black spike at the midpoint?
Because it never saw one directly at the center.
It never saw, during evolution, it never saw a dropped pair that started directly above itself. And so under those conditions it never saw during evolution, even though it's obvious what to do, there's a 5-year-old child running out into the middle of the road and not looking in the direction of the autonomous vehicle. It's obvious what the agent should do in these conditions. It's not doing it. It says, I didn't know what to do. I never saw that situation before, right? A huge problem in machine learning. In my opinion, no one is anywhere close to actually solving this problem. And for real world machines, it can be a matter of life and death. Not for this experiment. Okay. All right. Any more questions about this one? All right. Perfect timing. The minimal cognition experiments is like the Olympics of evolutionary robotics. All right, here comes event number 2, self, non-self discrimination. Being able to tell the difference between self and everything else, which we're going to call non-self. We've seen this already. We've seen a robot grappling with this. What was that robot? Anybody remember?
Baby bot.
baby bot, right? It's completely blind. It could only see movement. It would see this blob suddenly move whenever it sends commands to the motors, and it figured out it could discriminate between self and non-self. Here's the minimal cognition version of it. We take that same agent we saw before, but now we're going to nail it to the bottom of the screen. So no more rocket thrusters. This agent has only one motor neuron. In its CTRN, it has one neuron assigned as the motor neuron, and that motor neuron controls one rotational joint that causes its little arm to rotate back and forth in front of itself, represented by the curved dashed line here. And at the end of its little skinny arm, they placed a little ball which would obstruct its vision. Yeah, so if I put my fist out in front of me, it also obstructs parts of my vision. They're going to drop a single object from the top of the screen. That object can fall straight down or at different angles, represented by the dashed straight arrow here. And that object, as it falls, can also obstruct the robot's vision. So in this little cartoon here, at this moment in time, the robot is seeing its own hand and it's seeing a falling object, but from its point of view, it doesn't know. It can't discriminate between self and non-self. All it knows is 10, 10, 10, 10, 2.3, 8.6. That's what, from its perspective, remember, at every point in time, it's getting these 7 numbers, which are the distances reported by the 7 proximity sensors, or the 7 distance sensors. Okay, so how are they going to evolve this agent to become capable of self, non-self discrimination? The fitness function, which again also has a typo in it, they're going to drop many different objects and evaluate each CTRN num trials time. So we're going to talk about P sub I, the performance of this robot. How well does it do at discriminating between self and non-self in the ith trial? It's going to get a lot of points. P sub I is going to be a large value if when the object gets to anywhere along this curved line, anywhere where the quote-unquote hand could grab it, the robot should rotate its hand and grab that object. So they're going to drop objects that hit anywhere in this radius here, anywhere along this semicircle. And the agent, again, can't tell us. It's going to show us that it can discriminate between self and non-self by interpreting these 7 numbers in such a way that wherever the object hit, it always rotates its hand to be there. If it couldn't discriminate between self and non-self, it wasn't able to interpret these numbers appropriately, it wouldn't be able to solve this task. It's okay if you can't see that connection. You can just take my word for it. It's got to be able to solve this task to exhibit this behavior. All good? Okay. All right. So what's P sub I? P sub I is 1 minus. So whatever this term over here is, evolution is going to try and make it as small as possible because we want P to be as big as possible. This term includes just one variable, theta sub I. Theta sub I is the angular error at the end of the ith trial. So if my arm is out here and the object hits right here, then it's this angle that matters. If the object hits here and my hand, quote unquote, caught it, then the angle between these two things is 0. We want to try and minimize that. Make sense? The rest of this is just a normalization term so that this term comes out to a value between 0 and 1. So this term over here is 0 if the agent catches the object, and this value is I guess pi over 4 is the worst it can be. It's pi over 4 if it does really bad. That's all we need for our purposes today. Okay, start out with a random population of CTRNs. evaluate them, so we compute p for each one of these CTRNNs, delete the CTRNNs with lower values of p, and make randomly modified copies of the CTRNNs with higher values of p, repeat again, again, again over evolutionary generations until eventually they obtained a CTRNN that had a p very, very close to the optimal value, whatever that was in this case, which I guess is 1. 1 is the highest that p can be in this case, and values near 0 are really, really bad. Okay, so what they then took out of this population at the end, the CTRNN with the highest p, which again, you'll have to take my word for it, was near optimal, but not perfect. It had a p that was very close to 1, but not quite 1. They took that evolved CTRNN, dropped it back into the agent a whole bunch of times, and this happened. They plotted on the horizontal here a whole bunch of trials in which the final object angle was at minus pi over 8, hit that semicircle at minus pi over 8, or hit at plus pi over 8, or the object hit directly above the robot. The vertical axis represents the final angle of the arm. The arm was either at pi over 8, 0, minus pi over 8, 0, or pi over 8. How did the robot do, armed with this evolved CTRNN? Pretty good, right? So optimally, the horizontal value and the vertical value should be exactly the same. The little vertical lines represent there's a little bit of error. Under different conditions, the robot didn't always exactly catch the object, but did pretty good. Okay. Let's see what this robot did. I mentioned I love the analysis that these investigators did. Some of these plots take a little bit to be able to parse them. This one is the most challenging one. So deep breath, here we go. Okay. Let's start in the upper left out here. You'll notice that there's a whole bunch of wavy trajectories. Like a few minutes back, each wavy trajectory here represents one trial with this one evolved CTRNN. We're looking at the best CTRNN. So we're looking simultaneously at the average behavior that evolved CTRNN causes in the agent under different conditions. Okay. So there's one set of trajectories that start up here and a second set of trajectories that start up here. What is the position of the trajectory represent? Let's see. These are agents, right? These are trajectories representing the position of, the angle of the arm. So the further to the left any given point on a trajectory is, the further the arm was to the left. Any point on any given trajectory that's far to the right, the arm was rotated to the right at that point in time. The vertical axis here represents time. You'll notice that all these trajectories end at the end of time, which is when the object gets to the agent. They all converge on 0 here in the horizontal center. These are cases in which the robot always ends up with its arm directly above its head. One additional experimental detail, they dropped this object from lots of different positions that was falling at different velocities and different angles, but all those objects eventually hit directly above the robot. So we can see that the robot is doing a pretty good job. The robot is always, quote unquote, catching the object right overhead because that's where the object ends up. Everybody understand the shapes of the trajectories? Okay, let's talk about the brightness or the grayscale of the trajectories. The color, the grayscale represents the trajectories are shaded according to the initial angular position of the object as indicated at the top of the plot. The initial angular position of the object. So dark colored trajectories were dropped, the object was dropped minus pi over 8 radians above and to the left of the robot. Light-colored trajectories, the object was dropped pi over 8 radians up and to the right of the robot. It's hard to put these two pieces of information together. So let's do a few examples. You'll notice that over here, there is one light-colored trajectory. It's a little hard to follow on here. It ends up over here, and ends up back over here. What does it mean for a light-colored trajectory to start up and to the right in this figure? What does that represent about that particular trial? Trajectory that starts on the right and it's light-colored.
The arm was initially to the right and the ball was also initially to the right.
That's correct. That's right. So they start by cranking the arm to the right, which is the position of the trajectory, and then they drop the object from above and to the right, which is the color of the trajectory. It's hard to see here, but underneath some of these light-colored trajectories are darker gray and black trajectories. So there is actually a black trajectory that starts up here. What does that represent? What experiment does that represent? You sort of see it pop out from underneath the light-colored trajectories here, and off it goes. What does it mean for a black trajectory to start up and to the right?
The arm starts to the right, the ball starts on the left.
Absolutely. So the position of that trajectory on the right tells us that the arm was initially cranked to the right at the beginning of the simulation, and the object was dropped from above and to the left. Always takes me a little while to get all this loaded into memory. All good? Okay. What's happening? What is the robot doing in general? We know what it's doing at the end. Catches the object.
Kind of waving back and forth until it.
It's waving back and forth for sure, right? It's the most obvious thing of this plot. It doesn't have its arm to the right and the object starts falling from above left and it goes, or sees the object up to the left, watches it, and puts its arm right in the center and waits to catch the object. It's not what it's doing.
It's sort of sorting the darker paths over to the left, where the ball and the arm are starting on opposite sides, sort of sorting them out. And then sorting them out.
It looks like it's sorting it out, right? So the other observation you can take from this plot is like there's clumps of trajectories. This picture, in theory, could have looked like a big ball of spaghetti. There could have been lines all over the place. But you're right, it's kind of sorting. It quote unquote, it looks like it's sorting different percepts, different situations into categories, and then acting similarly or identically in those different situations. That's what it looks like. Again, I'm putting all this in scare quotes. Whether that's what it's actually doing inside its evolved C-N, who knows? Why? Why all the waving back and forth?
Is it because it's sensors, so it's like it sees it, then it misses it, and it sees it, then it misses it?
Maybe sees and misses it, but why would you want to miss it? Maybe, why doesn't it just move the arm out of the way and watch the object? It's waving it back and forth. It's obstructing its own vision. It doesn't seem like a very smart strategy.
The waving back and forth seems to get tighter. Maybe it's trying to kind of calibrate itself to the trajectory of the robot.
Calibrating itself relative to the trajectory, right? Now, it's impossible to say, but it looks like all this waving is helping it understand that some of the low floating point values, some of its obstructed vision is because of self, and maybe it can learn that by moving things around. When I move my arm like this, the numbers change in this way, but the numbers are also changing in a different way. It seems likely, although hard to say, that all this waving has something to do with discriminating between self and non-self and figuring out then what to do about it. possibly.
It seems like a little reminiscent of, trying to catch a pop fly or whatever. Like, if your glove is in between your eye and the ball, then, and you can like verify that at different points in time, but like particularly right as it's about to hit the glove, then it's going to hit the glove. Like,
That's absolutely. So it kind of looks like a familiar kind of thing to do. Moving your arm out of the way and kind of looking and waiting and waiting and waiting, then at the last second doesn't feel like a really good thing to do. And that's definitely not what's going on here. Also not really great to like obstruct the thing that's moving at you at a very high velocity, because then you actually don't really know. I mean, you know generally that it's somewhere out there, but you don't know exactly where it is. So it's possible that this waving is also striking a balance between learning enough about self to de-obstruct your own view and know enough about self to get the glove, so to speak, in front of the object and quote unquote know that that represents a good situation. Sometimes. If the ball is moving obliquely to you and at a certain point in time you don't see it, doesn't mean that it suddenly isn't going to pop back into your field of view and hit the side of your head.
What's the limiting speed of its ability to change the angle?
What's the limiting speed? I don't know. It's hard to say whether this is like the maximal speed at which you can wave back and forth. I'm not sure. Regardless, it's doing a lot of waving. If you want to learn about the world, in this case specifically, you want to learn about self and its differences from non-self, you got to move around. It's a very zoo-chauvinist thing, right? Privileging animals over plants. We move around. Movement is awesome. It's a good thing to do. But generally speaking, yes. In our world, there are fast-moving objects that we care about, like toddlers running out into roads, and moving and seeing how our sensorium changes when we move relative to other things that are moving, super important. Other questions about this one? Okay, this is a fun one. Event number 3, short-term memory. In this case, they're going to evolve the agent to exercise it, to use it. So how do they do that? We go back to our robot moving left and right along the bottom of the screen, so 2 motor neurons controlling 2 rocket thrusters. We again have 7 proximity sensors, but they're now drawn as dashed lines for a very good reason, which is the moment that the robot starts moving, the proximity sensors shut off. So this is an agent that can see what's going on, but the moment it starts moving, and even if it stops moving again, it can't see anymore. So the investigators from outside are going to partition sensation from action. You can do one or the other, but not both at the same time. Okay. They're going to drop individual objects from the top of the screen. The objects can fall straight down or they can fall at an angle, and you can guess, you've probably guessed the game at this point. The fitness function is going to select for, in this case, minimizing D sub I, minimizing the horizontal difference between the robot and the object's final position when it hits the ground. So basically, the agent has to catch the object or be where the object is when the object hits the ground. Okay. All right. So imagine you are this agent. You haven't moved yet. The object is here, and it's falling either here or here. What do you do? You could not move and keep seeing, and these 2 proximity values would change at some rate, and presumably an evolved CTRN can quote-unquote interpret those values and quote-unquote know what to do. The object is falling in this direction at this speed, and okay, I'm going to start moving to the right in a certain way that I'm going to get to the object in time to catch it. Or you can say, oh boy, I'm not quite sure exactly how the object is falling, but it's falling really fast. I got to start moving now. I can't wait to gather any more information about this object. I got to get moving. I know I'm going to be struck blind the moment I do, but I don't have time to waste. Somebody was mentioning like time windows in which you can determine what to do. Again, for creatures that make our living by moving around, this happens a lot of time. Fitz gave the example of catching a fly ball, right? So there's an object coming at you really fast. You're not quite sure. You do this and you close your eyes. You hope for the best, right? You move quickly and hope that that's good enough. So among other things, this agent is going to have to evolve the ability to strike a balance between perception and action. All good? Okay. Same deal as before, create a population of random C-tier and N's, evolve them so they get better and better at minimizing D sub I. At the end, we take the single C-tier and N with the highest value of P that minimize D sub I the best, and we plot its behavior as follows. So final object position, this is where horizontally the object hit the ground. So over here, the object hit the ground at the bottom left of the screen, and over here, the object hit the ground at the bottom right of the screen. Vertical axis is the same thing, but for the agent. What was the agent's final horizontal position when the object hit the ground? How did the robot do? Is it optimal? Shouldn't even have to look at the plot at this point. You're never going to see optimal behavior. Is it doing terribly? Kind of okay? Pretty good?
Again, suffering at the extremes.
Suffering at the extremes, right? So it's not doing very well when the objects hit lower left and lower right. And where else is it struggling?
Is the robot always in the middle?
You mean, does the robot always
Or is it-
start
yeah.
in the middle? Yes, the robot always starts in the middle. Where else is it struggling?
It gets it right when it's directly above it, but when you go when it's a little bit from not directly above it, then it gets pretty iffy.
When the object hits,
Yeah.
not quite at the bottom center of the screen, a little bit to the left or a little bit to the right.
It's not quite sure what to do.
Yes, not quite sure what to do. Okay, so again, not surprisingly for an evolved or trained machine, generally it does well, but kind of struggles with some of these extremes, some of these situations. Let's start with the extrema. Anybody have any guesses to why it's having a hard time out here? Remember the particular disability that this robot is dealing with.
If it's like sort of as far away as possible from where the robot originally starts, it's going to have to spend more time moving to get to it, which means less time that it will be able to observe the trajectory of the ball.
The robot starts at the bottom center of the screen, and in these cases over here, the object is going to hit bottom left. Now it's not clear. The objects that hit bottom left, they could have started at the top left and fallen straight down, or they could have started top right and traveled diagonally and hit bottom left. But in both cases, the robot's going to travel a fair distance to get there. Kind of tricky, possibly.
I'm not sure exactly how the sensors are designed, but looking at the diagram, if it's on the extremes, it may be getting less sensory input of it, so it's harder to determine.
It's getting less sensory input because?
Because the sensors are more focused towards above it and around here, not as much out here.
Exactly, right? So this robot doesn't have very good peripheral vision. It can't see very far to the left or very far to the right. It could if it starts moving. Oh, wait, no, it can't, because the moment it moves, it shuts off. This plot is still for the same evolved C-tier and N. It's going to shed a little bit more light onto these particular peccadillos of this agent. Okay, let's have a look at this figure. On the horizontal axis here, we have the horizontal position of the robot relative to the object. So minus 50 means the object started falling 50 length units up and to the left of the robot. 0 is the object starts falling directly above, and 50 is the object starts falling above and to the right 50 units. Okay. The vertical axis here is vertical position of the object. So it starts at 175 units above the agent, starts falling, and then hits the ground here. Again, each trajectory corresponds to one trial with the evolved C, T, and N. The brightness of the trajectory represents how well the robot did. So black represents the robot did the right thing, and gray represents wasn't great. Tell me about what the robot is doing under these conditions. What's happening?
When it's close to the center, when it like starts closer to the center, it looks like it's not really moving, and then when it gets really close, it maybe scooches a little out of the way almost.
So the vertical segments of these trajectories represent the robot not moving, right? The object is falling straight down, and the robot is staying still. Horizontal position between these two things is not changing, right? Diagonal lines represent the robot is moving. The diagonal lines, each individual trajectory always has the same slope, which represents the robot is moving at a constant velocity and then grab the object. There's none of this going on, which indirectly going back to the other experiment suggests the sweeping that we saw there was the robot trying to improve its ability to sense its world. Here, when it's moving, it's blind, so there's no point in moving back and forth, sweeping underneath. It always moves at a constant velocity in all the trials. All the slopes of the diagonal segments of all the trajectories have the same slopes. The robot always moves at the same speed, sometimes to the left, sometimes to the right, for a longer or shorter period of time. From an engineering point of view, this is nice, efficient, makes sense, simple, predictable. I'd like to be around this kind of autonomous vehicle, except for these conditions out here. What's happening here? You'll notice that if you visually follow any of the gray trajectories, they don't reach 0 on the horizontal axis. The robot, quote unquote, misses the object. It was wrong about where it thought or, quote unquote, predicted the object was going to hit. Why? These are the extrema. Why is this difficult for the robot?
It looks like at that speed it just couldn't move to 0 fast enough.
Maybe. Look closely. Sometimes it actually overcompensates. It goes past the object. Like this one. It was moving fast enough. It actually got there and then overshot the object.
There's less time to think about it.
Less time to think about it. Let's go back. Remember the sensing ability of this robot. It's got a cone of perception pointing up towards the top of the screen, but we're dropping this object either far to the upper left or far to the upper right. Now, the robot actually still gets pretty close. So presumably the robot can, quote unquote, see the object, but as was pointed out before, only during a very, very narrow period of time. If my cone of perception is pointing up and an object starts falling from the upper right, it's very quickly going to pass outside of my cone of perception, and by definition, I can never see it again. Even if I start moving so that my cone of perception would have swept underneath the object, I'm blind because I'm moving. So the robot has to, quote unquote, make a decision in a very short period of time, and it seems it does okay, but not great, right? Same with us. You're looking this way and you suddenly see some object or some blurry thing coming at you very quickly. You've got about 1/10 of a second to decide what to do with all the muscles on the left side of your body. You might not get it right, but you do kind of generally the right thing. So we've been beating up on these robots quite a bit. Let's pat this robot on the back. It's doing the best it can, given the finite abilities of its sensorium. We can't perfectly sense and perceive everything in our world. We act the best we can given the limited perception that we have. We can see pretty well. Things are kind of blurry. There's a certain frame rate to our visual system. Our visual system is excellent, but not perfect. Okay, we've got 5 minutes left. I'm going to skip over this one. I want to spend some time on the fourth and final one. We saved the best event for last. These are seemingly simple building blocks. Perceiving affordances, discriminating between self and non-self. You figured that out when you were about 3 months old. That one's kind of easy. Thinking and acting separately, you can do that. You can sit here quietly and think about what you're going to do about your next class before you actually act it out. Easy. This one, not so easy. I don't know about you, but I still struggle with this one, selective attention. In this case, our agent is going to have to deal with multiple things happening in its world, and it's going to have to attend or pay attention to those things, and it's going to have to attend to multiple things and switch between them. It's going to have to select what to attend to. Hopefully, at the moment, most of you are selecting to attend to my voice or what's up on the screen, but from time to time, you might mentally switch out and think about your next class or what you're up to tonight, and then hopefully your attention comes back. Your cell phone rings, you feel it ring, you wonder who it is that's calling you, your phone has grabbed your attention, you try and grab your attention back, hopefully to attend to the class. We're dealing with this all the time. As we're all collectively learning, one of the drawbacks of an advanced technological civilization is there are more and more things vying for your attention, and you're more tired at the end of the day because your brain is trying to figure out which of all these things to pay attention to and deal with at what time. It's not an easy thing to do. Yeah? Okay, so I'm talking up the difficulty of selective attention. We're going to strip that task down to a minimal version. We've got our robot moving left and right along the bottom of the screen as normal. We're now going to drop two objects from the top of the screen, but they're independent, unlike in the affordances task. They're going to fall at different speeds and in different directions. So the dashed black lines are representing the direction and speed at which these objects are falling. If you were this agent at this moment in time, and your task was to catch both objects, what do you do? At this moment in time. Go for the closer one first, this one. Okay, so you have selected to attend to the closer one, and then figure out how it's falling and adjust your rocket thrusters to make sure that you're there to catch it when it hits the ground. If you're lucky and if you bet correctly, it is going to hit the ground first. You catch it, and then what do you have to do next? You have to go to the next one, but before you go to the next one, you got to figure out where it is. Where is it falling, right? Maybe I go this way. Oh, it was over there. So I have to now select to attend to this one, figure out what's going on, and then go and grab it, right? Tons of video games that are based on this principle. It's fun and agonizing depending on circumstances. You'll notice in this cartoon example that this vector is longer than this vector. So good guess, simplest thing is just go after the closest one. This cartoon example is cooked to show you that actually, if you think about it, this one is going to hit first. It's further away. Ultimately, it's going to be the one you have to pay attention to first. So not easy. How do you figure out which one to attend to and which one to go chase after?
You have to balance the distance and the speed.
Distance and speed, and one more thing.
Angle.
Yep, the angle at which it's falling. So there's a lot of information here that the agent is going to have to juggle. We're still dealing with a minimal building block of cognition, but even in this minimal form, this is not an easy task. Or depending on how we drop the pairs of objects, we can make it easy, make it medium, make it hard, make it super hard. And we're going to see that next time. We got 2 minutes left, so let me just give you a little bit more details. We'll set the stage and then deliver the punchline next class. Again, we're going to evolve populations of C tier and Ns to maximize P, or minimize this term. This term is going to try and minimize di1 and di2. di1 is the horizontal distance between the first object's final position and the agent's final position. So 1 is the object that hits the ground first. By definition, that's always going to be object 1. But object 1 might have started further away. This might be object 1. It might have started further away from the robot, but it's the one that's going to hit the ground first. di2, horizontal distance between the robot and object 2 when object 2 hits the ground. Grab object 1, figure out where object 2 is, and grab it. So far, so good? Okay. I think we will put a pin in things here for today. You have a quiz due tonight. You're working on assignments 5, 9, and or 10. See you on Tuesday.